So in question 1, we have these two blocks with masses m and 3m. Arranged in the setup, we have an ideal spring. We compress the spring by some distance xc, and we have this block A traveling firstly in this region without a coefficient of friction. Then we have this region with distance d, which has a coefficient, and then it will collide with block B and stick to it. And in part A, we need to derive an expression for the speed v of block A at time t1. So right before it has entered the rough region over here. So in this region, we have energy conservation. So we can simply say that the initial kinetic energy, so the energy stored in the spring, in the initial, the elastic energy will be equal to the final kinetic energy at this point, as the elastic energy is converted into kinetic energy. Therefore, elastic energy is simply 1/2 k times the compression squared, and this will be equal to the final kinetic energy, so 1/2 mv squared, which we can rearrange for v. So we get that v is equal to xc multiplied with square root k over m. And then for part 2, we need to derive an expression for the speed VAB of the two blocks immediately after the collision. So we know how much kinetic energy it has here. It will lose some kinetic energy in this rough region. It will have a final kinetic energy over here, and it will collide with that kinetic energy with block B, where energy will not be any more conserved, as we are not told that it is an elastic collision. They stick together, so it's not elastic. However, momentum will be conserved, which we will be able to use here. So what we can say is that in this region, the acceleration of the block will be equal to minus mu times g. So if we think about the forces that are acting here, the only horizontal force acting here is the frictional force, which is mu times, so the frictional force will be mu times the normal force. The normal force is m times g. And since this is the only horizontal force acting on it, we can say that this is the net force in the horizontal direction. Therefore, the m's will cancel out and we get A is equal to mu times g, and obviously in the negative direction as the frictional force is pointing to the left. So what we can say in here is that the kinetic energy right before the collision with block B will be equal to the initial kinetic energy. So what we have solved for over here, we have the speed before the collision. So we will have 1/2 times the mass times our final speed squared. So right before the rough region. And from this, we will have to subtract the energy we lost in the rough region. So we know this is the acceleration. So we can simply say that the work done by the frictional force will be simply this multiplied with the distance, as the work done is the force times distance. So it will be mu mg times the distance we have traveled. And this will be equal to the final kinetic energy, 1/2 mv2 squared. Let's say for this speed here is v2. So if we rearrange this for v2, we get that this will be the square root of k xc squared over m minus 2 times mu times g times d, like this. So now we know the speed, and what we can say is that in this collision, momentum is conserved. So if momentum is conserved, that means that ma, so the mass of A multiplied with the final speed v2, will be equal to their final momentum, which will be a mass of total of 4m. So 4 times m of A, or simply just m. So you can simply say this will be m times v2 multiplied with their final speed VAB. So all we need to do here is rearrange for VAB. So what we'll have is m times v2 divided by 4m. So that will just be this speed v2. So we can write on the bottom we will have 4m. And we will have m times the speed v2, which we have already solved, which we have just found with the energy conservation, like this. So we can still simplify this a bit. We can cancel out the m's. So we just get this expression, UGD.